How is it going, everybody? Tonight, what I'm going to do is I'm going to put together a video that we haven't quite talked about yet, but as you are preparing for GIS Day next week, I thought it would be helpful. I will go slowly, and these are the things that we'll be talking about during our last class, but I thought since you all are mapping and getting ready for that it would be good to have that now. Also, I want to point out that to get into the spirit, you hear the Bee Gees playing in the background. So you know that this video, in which we will cover what's known as point pattern analysis, has groove and it has feeling. And so relax and enjoy. So what we're going to start with is I'm going to perform these analyses, or illustrate these analyses kind of in steps. But what we're going to do is we're going to assess the pattern of point level data of homicides or missing persons in this case. And we're going to determine is there clustering, and if so, where? And then we're also going to create hotspot maps. And so that is the process. So the first thing that we're going to do is I just opened this Boston neighborhoods shapefile, this layer, but I also wanted to, I also almost forgot. We're also going to calculate spatial descriptives and talk about how those can be useful. But more than anything, we just are going to be looking at the distribution of points and performing a point pattern analysis. So for example, from the crime incidents, I selected missing persons, and I'll talk about what this adjusted and unadjusted stuff is in just a sec. But just know that these are the reported missing persons in Boston between the years 2012 and 2015. What we also can see here is that there's something like almost 5,000 of them. So we have a fairly large sample size. And so the first question that we want to know is, we see this distribution across the city, and we see that it appears that there are more homicides in some places than others. But what we want to establish is whether or not, or the degree to which we observe clustering, or in terms of the points, if the points tend to be closer together in space than they would if all of the events were distributed spatially equally across the city. And so that's the way that it calculates this, is it measures the average distances, and then it calculates what the maximum distance would be, and performs a z-test, or a test of significance for the difference between those two values. And so that'll be clearer in just one sec. But the way that we're going to do this is we are going to use the ARC toolbox. And what we will also see is that we're going to use the spatial analyst tools in a few minutes, but we want to focus on the spatial statistics first. And then specifically, we want to look at analyzing patterns. And then we're going to click on average nearest neighbor, because this is what's referred to as a nearest neighbor analysis. And what we will include here is we want to look at the missing persons. And here, the distance method, we could we're going to leave it, we could change it. We're going to leave it as it's at its default, and we'll click generate report. And so what's going to happen is it's going to perform this analysis, and we're going to be looking for the results from the statistical test. And so what we will see here, you can see I've run a few of these, but what we see here is we see the nearest neighborhood ratio, and then we see the z-score, and we can also click on the report. We had a report created, and you see it creates this HTML page. And what we see here is that we have a value of -100, which is a z-score of -100. And so you'll see that on the negative side, that means that these events happen closer, right? So we have evidence of clustering. Also a z-score, anything greater than 2 is statistically significant. And so what we're seeing here is that our clustering is very, very unlikely, or we'd be very unlikely to observe the outcome that we did if there truly is no clustering of missing persons. And so I'll close that super quick. So the first thing that we did again is in the big picture, we have this distribution of an event. In this case, it's missing persons. And then what we do is we just want to test the extent to which there's evidence of clustering. Criminologically, sociologically, social psychologically, all of those disciplines have reason to expect that events are not distributed equitably across place. Disorganization theory, for example, argues, right, that crime is a function of the characteristics of places. And so we have reason to expect that there's clustering. In this sense, we're just kind of documenting it. And we can perform that same test again on the homicides in Boston. And what we should see again is if we open up the report, we see here that for homicides, again, we have a z-score of -22, which means that we are well into the tails of the distribution. And so that means that we have a statistically significant result, or we can reject the null hypothesis of no clustering and accept that there is. And this is really not a terribly big surprise. In a sense, it would be more unlikely if we didn't find clustering, at least around criminological outcomes. So that's the first part, right, where we just test, is there clustering? The next thing that we can do is we can calculate spatial descriptive statistics, and there are two that we're going to look at. And the first one that we're going to look at is the mean center. So what we're going to look at is, where does this distribution concentrate spatially? Where's the average, the spatial average, if you will? And where we will find that option is under the measuring geographic distributions, again within the ARC toolbox. And you'll see we have a whole bunch, not a whole bunch, we have a number of options. And if we simply pick mean center, what we're going to pick from the drop-down menu, if we start with missing persons, and you see it will write out a shapefile into this geodatabase. That's fine. We can leave that at its default. We'll leave all of these empty, and we'll click OK. And this should not take a terribly long time. But what it is, it's measuring it's averaging out all of the latitudes and all the longitudes, and it's generating a value here, which is the mean center for the distribution of missing persons. What we can also do is calculate a measure of variability. This big circle looks kind of silly to me, so I'm gonna change it to something different. We'll use this sign. Kind of looks like the chili peppers, so we will take it. There's no way. And I will turn off. So what we have here, this is the mean center. So in a sense, where does what the average a missing person, right? If we average out all of the locations, this is where we would end up. And also keep in mind that just like the arithmetic average, the spatial average is also influenced by extreme values. So if we had spatial outliers, that can throw off the location of the mean in the same way that extreme values can inflate or deflate the arithmetic average. The next thing that we're going to do is we're going to click on this directional distribution. And what this calculation does is it provides a measure of variability, of spatial variability, that is. And so we will get a sense of not only how over how wide an area is this distribution of missing persons distributed, also the direction. So we'll get a sense of, is the distribution tend to run more north and south or more east and west? Like, so how is it oriented, and also how large it is? So both of those things are going to be, information about both of those will be provided. So if we click on the standard deviational ellipse, and we will also then, if we stick with the missing persons, and one standard deviation is fine. So this is how over how wide an area is one standard deviation from that spatial mean, and know that the same kind of quantities apply, right? So if we go out one standard deviation, that will include a certain amount of the distribution, so roughly 2/3. If we go out one more standard deviation, we will include up to a little over 95% of the distribution. So one standard deviation is fine for our purposes. We'll also leave this at its mean, or at its default. And what we end up with is information about not only the mean, but also we see a north-south orientation. It's not, it covers a lot of the city. And if we were to click on the distribution itself, you see, as it should, but this information about the spatial descriptives tells us, provides us some information that we would not necessarily be able to get just by looking. In fact, we wouldn't be able to get if we wanted to identify, for example, the spatial average or estimate the spatial variability. We wouldn't really be able to do that just by looking. We can get a sense of where things concentrate, but we don't have precise measures just by looking. So we now have information that A, is there clustering? Yes, of missing persons. And then B and C, I guess we know, where does that distribution sort of center, right? Where is it anchored, and how much variability is there? And just like with the standard deviation generally, when we have smaller standard deviations, that also suggests less variability or a more compact distribution. What I want to also illustrate is that these measures can be very useful for the purposes of comparison. And so what I mean by that is we can compare, for example, two different types of crimes to examine the extent to which their distributions follow a similar, or to what degree they follow a different spatial patterning. And so I have an example of that I will go over, and you will see that I have some homicide information for the city of Boston. I'm going to turn off the missing persons here. And you'll see that I have information about all homicides that occurred in Boston. And then I also have information about homicides that have been solved or are cleared by arrest, or the person who they believe did it is no longer available, maybe passed away. So these are closed homicides, and we have the open or unsolved events too. So what I'm going to do is compare the spatial distribution of these two homicide outcomes to see the extent to which they concentrate in similar places and whether or not they have similar spatial variability. And so let's see how that looks. So the first thing that we're going to do is we'll open up the ARC toolbox and we'll click mean center. And what we're looking for here is we want to look for, let's start with all of the open or unsolved homicides. We'll leave all of these at their defaults. Hold on one quick sec. Okay, sorry about that. So we'll leave that at its defaults, and we will click here. And let me turn on. So we're starting with the open homicides, I believe. And so what we have here is we have the spatial mean for the homicides for which that have not been cleared or had not up through, I think, 2020. And then what we're going to do is we're going to calculate the standard deviational ellipse also for the open homicides. And so now we have information for both. And again, the information that we see here is consistent with what we're seeing in the distribution itself. It does run along a north and south. It does have a north and south orientation, and we do see some clustering here. So it makes sense that the center correlates with where there are concentrations, or what appear to be the highest concentrations. We can also then calculate those same values for the closed homicides, or homicides that have been cleared or through arrest. And so the mean center we will use. And so what we see here initially, let me turn on closed homicide. So what we see here generally, and again, the mean and standard deviations are interpreted the same, but it appears that the closed homicides have a different mean location, and also you'll see the variability, right? The closed homicides are not as concentrated spatially. And so if we compare them, and I'm going to turn these off because I already created maps that I think would be a little bit more intuitive. And so what we see here, that the darker green, those are the open homicides, and you see we have they have a different mean center, and also, right, the homicides that are not solved or that remain unsolved concentrate spatially in a much smaller area than those that are solved. And you also see the mean center is moved, is north a little bit. And again, that's owing to the distribution itself, not only having a larger variability, but the location, the average location, is in a more northern spot. And so if we look at the closed homicides, that is also consistent with our visual, the intuition that we may have by looking at the distributions. And so again, would theory expect that to be the case? It's hard to argue why we would expect a differential distribution of solved and unsolved homicides. But in any event, we now know that they both follow a similar orientation, but open homicides are concentrated across a narrower range spatially. Finally, what we're going to talk about is we can now know that there is clustering. We know the spatial descriptive information that are interpreted in a very similar way to descriptive statistics generally. And now what we're going to do is we're going to create what are referred to as hotspot maps or cluster maps. And the way that we do that, I'm going to turn off these spatial descriptives. The way that we do that is we are going to need to make sure that we have one of the extensions enabled, and it should be enabled. If it's not, we'll have to enable it on the university machines, but I think they're enabled by default. So just hold on one second. All right, so the first thing that we have to do here is apologize, because I was reminded that I thought the Bee Gees sang the Grease Lightning song, but that was so wrong. I understand. So my apologies to you. I did put the Bee Gees on Saturday Night Fever. So, wow, that's embarrassing. So sorry about that. But anyway, to get back to the mapping part, what we have to do now is what we're going to look for is we have to make the analysis that we're going to conduct requires that we have one of the extensions enabled. And so we can check that easily if we click on the toolbox, and you'll see that we have a spatial analyst listed here. And so what we're going to be looking for is density and then kernel density. And if you get an error message that says tool not licensed, and you're probably going to be like, damn, sorry, Stowell can't do that. What we're going to have to do is we'll click out of this, and then what we can do is we can go to customize and then extensions, and we want to click spatial analyst. So one more time, if we go under customize and then extensions, click spatial analyst and then close, and then if we go back to the toolbox and click on spatial analyst and then density and then kernel density, we should be able to open up a dialog box. And so that's what we're looking for. So the kind of maps that we're making are called kernel density maps. And these are maps that look at the frequency. So they're based on the counts, and it will find areas with the highest intensity in terms of location, and those will have a higher value on this scale. And what you'll also see is once these come up, what it's based on is a grid system. So essentially, though this analysis draws a rectangle around the city with a certain number of columns and rows, so little boxes, and each box is assigned a value, and based on the number of events in that area and the areas around. So it considers all of these factors. So let's create a kernel density map, or I'm going to create is a kernel density map of missing persons, and and so I will click on missing persons adjusted, and here's where I will show you why it is important. But first, let's create the adjusted missing person values. And so we're going to keep all of these at their defaults except for output cell size. And here, what we're going to do is we're going to add 3 zeros. And what we're doing is we're making this a smaller grid size, and that produces a more refined or more granular picture. And what we're also going to do is we're going to change this to geodesic, and then we're going to change this to square miles. And so once we have made those changes, we'll click OK. And what's going to happen is a new layer will be added to the map. And what that layer includes is the ranges. It's going to show a series of ranges around the area, around the city, with the darker areas, those with the highest concentrations. And so if we turn this off for just 1 sec, and then we click on the missing persons, and you see that this is an area with that had the mean, center, and the standard deviation of ellipse was in this area. And so what we see here is a pattern that is consistent with what we have already seen. And so these maps are very useful, but they're not always all that intuitive in terms of, right, you can't see the underlying city boundaries. And there are a couple of ways that we can get around that. One of those ways, and I'll show you both. The first way is we can turn on the neighborhoods. And then if we copy the neighborhoods to the layer above, and so it's kind of like the neighborhoods are overlaid on the kernel density map. And then if we click on the symbology and just make them hollow, what you'll see is we can kind of get a sense of the underlying, the distribution of the neighborhood boundaries looks like with respect to the densities. So that's one way that we can show the locations of the densities. Another thing that we can do is, and I'm just going to change these back to darker boundaries, and then I will switch the order here so that we and so what we can do also is we can change the display properties, and you see that the areas that we're most interested in are the areas that have the colors. So there's all of this space around this city that is there really weren't any or many events or any, and so what we can do is we can change the color here. Let's see. And if we, and I'll turn off this event too. And so if we were to, just by making that first layer see-through, we can get a sense of the distributional pattern of the events. Of course, we can also change the order as well as we did before. But again, what we're seeing here are the areas of the city that have the highest numbers of missing persons reported. These aren't rates, or they're not adjusted, but again, these are the values of these are the areas that have the highest frequencies. So let's also then we can do that same kind of calculation for the homicides. And so we'll do that in just 1 sec. Okay, so what I'm going to go through right now is I'm going to create a kernel density map again, but this time using the distribution of homicides. So I'll open up the ARC toolbox and click on the kernel density. And then the layer that we're looking for, I will use all homicides. We'll leave all of these at their default, and then similar to what we did before is we will calculate the you calculate the densities using a geodesic, or more of a not just as the crow flies, but really measures distance in a little bit of a different way. And so first thing I wanted to show is when we calculate based on the geodesic method, we need to set the units correctly. And if we do not, we'll get an error message that tells us that we don't have the right measurements set. And so in this case, we'll change that to square miles, and then we'll click OK. And again, what's going to happen is it's going to create that the program will create a new layer that has it has the information about the areas that have the highest numbers of homicides. And so we can change the color and make clear just that first layer, and we'll see we now have a map that shows the distribution of homicide, the frequency, the areas with the highest numbers of homicides in the city over the past decade. There are a couple of other things that I wanted to show you. One is a display, a way that we can display the information, and specifically something that I think can look provide a very kind of a very smooth and kind of a map that is easy to interpret is if we click on the stretched feature and then click apply and OK, you see we now have a map that the colors are a little more nuanced, and we can again overlay that distribution with the neighborhood boundaries as a way of illustrating the areas that have the highest concentrations. So again, what we did is under symbology, I click stretched, and again, if we wanted to use quantiles, or we can do that. It just produces images that look a little bit different. It's the same, it's based on the same information, so nothing's different. It's more of how are we going to, or how do we want to display that information. And so again, what we have the density map of missing persons, and we have the density map here of homicides. And I think that can be useful in the sense of giving not only descriptive accounts, but an account of a distribution, or the qualities of a distribution that look, giving the qualities of a distribution that's based on more of a statistical or a quantitative analytical approach. The last thing I wanted to show you, and I saved it for last only because I want you to I wanted to show you successful cases before we looked at unsuccessful cases. So if you are working on creating these kernel density maps, and again, we're going to be talking about the spatial descriptives and the kernel density maps in class this week, but I thought some of you may really want to include them in your as you're preparing your posters now, and at least if you did, I wanted you to have the opportunity. I think they can be really helpful and really useful. But in any event, if you decide to use them and you end up with a kernel density map that looks very strange, that it can't be correct, oftentimes that's due to having some spatially anomalous observations. And so I'll give an example of what that looks like. Okay, so here is an example of what I was talking about. And when we are going to conduct the spatial descriptives, or if we're going to create a density map, it's important that we make sure we get rid of any kind of spatial outliers or spatially anomalous cases. So for example, if we turn on all of the missing persons, and what you'll see here when I open up the attribute table, we have 4,827 observations. And what I'm going to do first is I'm going to calculate the standard deviational ellipse here. And what we're going to see, if we calculate the standard deviational ellipse, and you'll see you might get some kind of screwy result like this. And if we zoom out, you'll see like, wait, like what? And these errors are common, but they're also very noticeable when they do happen. So if you get results that seem reasonable, then there's a good chance that you did this correctly. Also, if we, for example, calculated the standard distance, and so this is the standard deviation, but doesn't take into consideration the orientation. And so if we look at all missing persons, and then, so we're going to see sort of conflicting things. We'll get a successful result. We'll have a layer that's added to the map. But then if we don't see anything and we zoom out, we see like there are some cases that are way over here. And so when we have a situation where it looks like it calculates things correctly, but we can't see the results, a lot of times that's because there are some kind of anomalous cases. And so we'll also see that if we were to calculate or to create a kernel density map, and so what we'll see here in just a sec is that the map looks, the resulting density map is going to look super impossibly like, right? It's just impossible. There's no variation, or it might be that it's the whole city is covered by one color. And if we zoom out and you see, this is a clear case of having these observations. And the problem is because all of these calculations take into consideration every observation in the distribution. When we have ones that are, for one reason or another, aren't have odd coordinate information, it doesn't know what to do with them, so it includes them in the calculations, and the results turn out to be very strange, but also very understandable as to why something like this is going on. So I'm going to get rid of these, and then the fix here is again, if we look at the attribute table, you see we have 4,827 observations. A quick and easy way to select out, or to make sure that our analysis does not include those observations, is to click on the select tool here, and then we will just draw a square around the area of interest, and you'll see that we no longer, because the other odd coordinated, the observations with strange coordinates are really, they just probably have no coordinates, are not going to be included. So what I will do is I will right click on the layer and go to selection and then create layer from selected features. Let me just unselect this stuff. And what you'll see here is now when I open up the attribute table, we have removed a number of observations, and those were the problematic observations. And you'll see here, if we sort on longitude or latitude, we have all valid values, whereas in the unadjusted file, and not that this is just for the purposes of illustration, you see we have a whole bunch of these zeros and negative ones that are causing the problem. So we just need to get rid of those for the purposes of analysis. And to show you, when you look at the adjusted values that I used, you'll see that they have this based on that 4750 and not the 4800 and change. Anyway, those were the tools that I thought would be useful to have some exposure to. I encourage you to try them when we have point level data, which a lot of the groups are going to be using. These kinds of techniques are pretty straightforward, but also can be very powerful in terms of illustrating a point, particularly the hotspot maps. And a small point of fact is that the hotspot maps are very similar to the weather forecast maps that you see on the news every day. So those are all frequency hotspot maps based on what's called a raster process, or a grid process. So it looks at probabilities within certain areas. And so anyways, I thought that might be interesting. Also, though, those their hotspot maps are created for similar areas over time, which is something that can be done criminologically to look at shifting patterns of a distribution over time. But what that requires a lot of times is having a lot of data over many time points in order to, sorry about that. Sorry about that. That was Coco. She needs a little bit of attention, which is good timing because we're almost done here. Thanks everybody. And if you have questions or if you'd like to talk about these techniques, I will be available this week. I'll be around and have try to keep a pretty clear schedule so that we can find time to meet should that come up. Thanks everyone. Have a good one, and please be in touch with questions. Take care.